Last time we talked about mathematical induction and how it is a process to prove a statement true that involves a positive integer n. And we looked at the sum of the first n odd integers. We noticed a pattern that if you started with 1 and added your odd integers up to the nth term, the sum would be n squared. But noticing a pattern is not a proof. So we're going to prove this today using mathematical induction. There's 3 steps. And our first step is the anchor step. We need to show it is true for S1. So to start out, we're going to write S1. Really what we're trying to do right now is prove that the left side equals the right side. So S1 is the sum of the first term on the left side, 1. And on the right side, if we plug in a 1 here, we get 1 squared, which equals 1. So the left is 1, the right is 1, they match. At least this formula works for the first term in the series. Alright, our next step is the induction hypothesis. This is where we assume it is true for Sk. Now, it's just a different variable, but the idea is there's some letter out there, some number out there that we're going to call k, where this formula is true. So we find Sk. Remember, that means we rewrite our formula and plug k anywhere we see an n. So from now on in this problem, this statement is true. We follow this up with the induction step, where we need to show that Sk plus 1 is true. So we're going to write out Sk plus 1. All we need to do is put k plus 1 where each of these n's are. 1 plus 3 plus 5 plus 7. Parentheses outside are going to turn into brackets. Plug in k plus 1 here. So our goal is to be able to start with this line, our induction hypothesis, and end up with this line to prove that it's true. Now, to help us a little bit later on, I want to peek inside this problem. Let me show you what I mean. If we had the numbers 1 plus 3 plus 5 plus 7 all the way up to 31 plus 33, this is going to add up to 17 squared. Well, these dot dot dots, remember that means the pattern continues. I'm just skipping a bunch of numbers. But can I still figure out what would be the next number here or the previous number right here? Sure. This is really 1 plus 3 plus 5 plus 7 plus, let's see, 9. And what would come right before the 31? 29. Now, by showing more of the problem, am I changing what I get when I add them all up? No. This would still equal 17 squared. So let's do that here. I have all the terms written. One moment here. We have our first term, our second term, our third term, our fourth term. This is the k plus 1 term. So the term that comes right before it would be the k term. So to figure out what the k term is, we plug k into this formula. So we could write this as 1 plus 3 plus 5 plus 7. I'm going to insert 2k minus 1 plus 2k plus 1 minus 1. So I haven't changed what it's going to equal. It still equals k plus 1 squared. So as we go to do our problem right now, our induction hypothesis, this is going to be our starting point, And what we wrote here for our k plus 1 term, this is going to be our goal. So now that we've set it up, I usually like to just draw a horizontal line across the page to separate, okay, here's the setup for the problem. Now we're going to do some algebra and work through the proof. Start by saying, by the induction hypothesis, which is here, our starting line. So let's rewrite the induction hypothesis. 1 plus 3 plus 5 plus 7 plus 2k minus 1 equals k squared. So if we're starting here and we want to end up here, we need everything to match. If you look at the left side of what we have and look at the left side of our goal, they're almost identical. We just have this extra piece here, which makes sense because this is our first k terms and this is the next one in line, the k plus 1 term. So if I want this to be this, we need to add this in. But remember, if I add it to one side, I have to add it to the other as well. So we write adding 2k plus 1 minus 1 to both sides. What are we going to get? 1 plus 3 plus 5 plus 7 plus 2k minus 1, so that matches here, and then we add in the 2k plus 1 minus 1 equals, the right side is k squared, and then I'm adding 2k plus 1 minus 1. Okay, so now I've managed to get my left side to match the left side of our goal. Does the right side match the right side? Well, it doesn't look like it yet, but that's our final job, to rewrite this so it equals this. So inside of our brackets, we could distribute the 2. Get your like terms together. And then factor. Since they're the same. And there we have it. Now our right side here matches the right side here. So think about what we did. We started off with a true statement. We said, you know what, there's some number k out there where this formula works. And all we did was applied algebraic steps and found that if this is true, then for k plus 1, the formula is also true. We just lined up our dominoes and made sure that each one would knock the next one over. It was also important in that very beginning that we knocked the first domino over. So if it's true for 1, now we know it has to be true for the next one, for 2, for 3, for 4, and all the terms. So we finish our proof with a sentence. Since the anchor step and the induction hypothesis were both true, our original statement was true. 1 plus 3 plus 5 plus 7 plus ... plus 2n minus 1 equals n squared. Now what I've done here is I haven't given you notes explaining induction. We've actually done an example together of what induction looks like. I'll zoom out here. All these words are necessary every time we do a proof. So what I'm highlighting here, I do require you to write every single time. And if you do that, it's actually an outline for you. Just have to fill in the math. Okay, we're going to work through one more example together, and what you're going to see is that all of this is the same, and we just fill in the math for the particular problem. Notice, to save time, I even went ahead and wrote it in already. So yes, you do have to write that every single time. Okay. So for our second problem, we're going to add up, let's see, we have another arithmetic sequence here. 5 plus 7 plus 9 plus 11, all the way up to 3 plus 2n. So remember what that means. We have our first term, our second term, our third term, our fourth term. To the nth term, when you add those all up, it's going to equal n times n plus 4. So we start with our anchor step, where we have to show it's true, at least for the first one. So if you look at the left side, what is the first term in the sum, or the first sum? 5. Look at the right side. We need to plug 1 for both of those n's. Let's see if this formula even works. 1 plus 4 is 5, times 1 is 5. So we're starting off good. Next, induction hypothesis. Assume it's true for sk. So what we do, we plug in a k for each of our n's. Induction step. We need to show sk plus 1 is true. So we plug in k plus 1. Notice that I'm being careful, and every time I put k plus 1 in parentheses, inside of parentheses, those become brackets. Now to make our lives easier, this is the k plus 1 term. I want you to show me the one that comes right before it, the k term. Three plus 2k. Also, if you want, this right side we could simplify. We have k plus 1 and k plus 1, but right here, k plus 1 plus 4 is k plus 5. So that's our setup. The induction hypothesis is where we're going to start. This last line, the k plus 1, that's our goal. But by the induction hypothesis, we rewrite this. 5 plus 7 plus 9 plus 11, 3 plus 2k equals k times k plus 4. And what you want to do is compare what we have here with the left side of the goal. We're missing this. So by adding 3 plus 2 times k plus 1 to both sides, what's going to happen? So we have our 3 plus 2k, and then we add to it 3 plus 2 k plus 1. Now notice the right side of my equation is k times k plus 4. So we add the left side matches the left side. We need to get this to match this. Distribute the 2. Get your like terms together. In this case, we factor again. And look, we got our right side to match the right side of our goal. So we've shown that if you start with the k term, do some algebra, the k plus 1 term is also true. And again, we finish with our sentence, and we're done.